And here we will move on to the compressed liquid. Okay, if the state lies in the region to the left of this saturated liquid line, then it will be a compressed liquid. Okay, inside compressed liquid, we will see that because liquid is essentially incompressible. Okay, so the properties would generally have a very little dependence to pressure, but it mainly depends on temperature. Okay, but in this case, the property will be very similar to the saturated liquid case. So we would find out the Y. Okay, we will approximate it to be the property at the saturated liquid at that temperature. That means the temperature that is given to U. Okay, for Y equal to U, V, and H, because we have just introduced these three properties. Okay, in general, this H, because is equal to U plus PV, so it will depend on V more heavily than V and U. So someone would suggest a more accurate method to determine the enthalpy is that not only do we include the saturated liquid value at that temperature, we need to also include this term. This term is what? Is equal to delta P times V. This delta P is the pressure at that point, okay, at the state, minus the saturation pressure at that temperature. And then take this delta P, multiply to the specific volume of this saturated liquid at that temperature. However, although it's suggested, in most cases, this method may overcorrect the values at a moderately high temperature and pressure. Okay, even it's 100 degrees C, experience tells us that this method will overcorrect. Okay, as a result, we will use this table in order to find out the properties in a compressed liquid state. Given the pressure and temperature, we can find out these three values by equating it to the values at the saturated liquid state at the given temperature. But how can you determine whether it's a compressed liquid or not? We will always do a comparison with the saturated state. That is, compared to the saturated liquid, compressed liquid has a higher pressure. Because at a higher pressure, it will compress more than the saturated case. So we will have a name called compressed liquid. Okay? P will be greater than the saturation pressure at a certain temperature. And it also has a lower temperature. If you consider the TV diagram, then you will see that before it gets to the saturated liquid state, it should have a lower temperature at a given pressure. And it also have a lower specific volume, lower internal energy, and lower enthalpy. Okay? For internal energy and enthalpy, intuitively it should be correct because we supply less heat than in the saturated state. So it should have a less energy content inside the compressed liquid. For specific volume, intuitively, you give less energy, so it would have a smaller specific volume. Okay? And this is the diagram for the temperature equal to 80 degrees C and the pressure at 5 megapascal. And we will see that for water, it will be in a compressed liquid state. So we will get this value at 80 degrees C, at this pressure, and then you can find out this internal energy, which is approximately equal to UF at 80 degrees C. Okay? Remember, you need to go to the temperature table to find out this value, okay, at 80 degrees C. Don't go to the pressure table, okay, otherwise you get erroneous value. Okay, so let's see an example to see how we can solve the problems involving compressed liquid.